Cool. Well, yeah, let's get started after the long hiatus. So, yeah, we can just kind of open these up and see. Let's just kind of go over what we. So the first thing we did was like the just overall message structure, and sorry. Yeah. So if you remember, this is kind of where we left off. We had this class message. Now we call it packet. So as you see, every class I like rename a couple things, which is probably extremely confusing for you guys. But we had this thing that just represents the kind of the general, the outermost layer of a Bitcoin network message. So if we go back to the protocol documentation, we go to common structures, message structure. And so, yeah, if you just type like Bitcoin Wiki protocol documentation, you'll be able to find this. You're going to be using it a lot. And so if you go to message structure here, remember, this is what has the magic, the command, the length of the payload, and a checksum for the payload. And so this is how any message on the Bitcoin peer-to-peer network will have this structure. And if it doesn't, your peers don't know how to read it. It just won't. They'll just hang up on you, and you won't be able to talk to them anymore because they don't understand you. So that's what we did in the first lesson. We made this Python class that could actually read those messages. But at the end, we'd have this payload, right? We'd read a payload, and we didn't really know what to do with it, you know? So if we, well, this one, I'd have to execute well, what the hell? Let's just run everything. Just run everything from this first notebook. Yeah, and so here you go. This is what we'd get. We get this string payload, and you know we don't really know what it means, do we? Like you can see the word Satoshi in here, right? But other than that, it just looks like gibberish. Would you all agree?
Yeah, there's a lot of zeros.
Yeah, a lot of zeros, a lot of X's. And so these are just, this is just a byte string in Python. And so we can, but that's cool. We like peeled the outermost layer of the onion, right? And then, so that was the end of class one. In class two, we basically tried to understand this in just the case that it was a version message, right? So this message is, the command is version. You know, remember there's like 27 different messages in the Bitcoin peer-to-peer network. Here's all of them. Version, Verac, adder, we'll have block somewhere here, TX block. These are the two that do all the heavy lifting, TX and block. And so lesson two was like, okay, let's decode this payload just in the case that the command is version, you know, because it's the first message we ever get, right? You got to do the, let's see. You know, when we do this, so this is the same Bitcoin Wiki. When you do the version handshake, right, this is how it works. Your peer says, or you say, this is URL, local. The other guy is R, remote. So you say, hey, this is my version. You send them a version message. Then the remote peer, the other guy, sends you their version message. So this is the first thing we ever have to read, is their version message, right? And so that's what we did in lesson two. We learned to, where is it? Yeah, here it is. So we learned to make this version message class that could take a byte string and basically turn a byte string into a version message with just this little chunk of code. So it was pretty nice what we did. We're now able to interpret version messages. And so if we look at the bottom here, this is where we left off, right? Basically all this does is it creates a socket, which is like a raw a way to do like a very low level communication between different computers or different processes in computers. And one of the kind of the default here is when you pass it an IP and a port, is it'll make a TCP connection, right? Which is the protocol that Bitcoin's built on top of. And so it creates a connection, and here you send it this raw version. And so one problem here is that I just give you this, right? So we should make this version message, right? This whole thing, we should be able to produce that, right? We're not able to encode the information we want. This is just hard coded, and that's not good. And then once we get the response, we just print it out and we're done. So we don't actually complete the version message, right? We receive the message. We do this step, right? This step. We send ours. Sorry. They send theirs, and then we stop here, right? There's two more steps. This step and this step in terms of sending messages that we need to be able to do in order to complete this handshake. And why do we want to complete the handshake? So that we can do with these interesting messages. These are the fun, interesting messages that we want to be able to send and receive. But you can't send any of these interesting ones until you do the handshake. So yeah, that's kind of where we left off. And so we have these two. We have this is what we have left to do. And we also want to not hard code the version number for this. We are hard coding this. So if we go to lesson 3, you'll see the start. I kind of explained there's three things we failed to do last time. Our initial version message was hard coded. We're not listening for our peers verac. Remember, it goes version, verac, verac. And we're not sending our own verac, the fourth step in the handshake. So yeah, and if we can just solve these three problems, then we'll basically be able to join into the Bitcoin peer-to-peer network just like a Bitcoin core node, like the C++ Satoshi's client that's been around since 2008. And we'll be able to join just like one of these nodes can. We won't be able to participate as meaningfully, but we can join. We're like an equal member of the network. We're just not as effective, really, because we still don't know how to do a lot of things. And so the first two problems, the last two problems, these verac is going to be really easy, because if you look in the protocol documentation, you go to verac, it's a pretty short thing. The message consists of only a, where'd it go? The message consists of only a message header with the command string verac. So you remember there's no table here. Remember how in the other things we've dealt with, there's this huge ass table that we have to learn to interpret? Verac doesn't have a corresponding table because verac doesn't contain any information. It's just, all it is like, yes, I got your message. That's all it means. So it's going to be really easy to deal with this. It's just a command, and to get a little more concrete here, when we go back to the message we built in the first thing, remember there's two attributes, command and payload. Command is going to be verac, and payload is just going to be empty. It's going to be this, just an empty byte. And so that's going to be a big improvement over having to, that's a lot easier than having to produce one of these, right? This is the payload for the version message, basically. Well, part of it is, but it's long and hairy. So the verac's going to be really easy. The part where we produce a version message, actually produce it ourselves, that's going to be a little trickier. And that's going to be the kind of the exact opposite thing we were doing in the first two lessons. Remember how we were always doing stuff like this? We were always doing from bytes or from socket, right? These are reading. We're taking some raw source of bytes and we're turning it into a Python object, right? This is called deserialization. deserialization means you take something that is sort of like a compressed format that many different people can understand. Like if you've ever done web development, the format is JSON, you know, like I could probably, you know, if you go to like Twitter, right? This is a little demo that I haven't tried yet, so it's probably not going to work very well. And if we can go to, let's see, where you want XHR, search for JSON. Yeah, so here you go. So here's, can you see this?
Yeah.
Yeah, so here's an example on the Twitter website, right? Like here's a big JSON message that is probably part of what's filling in the screen here. So there's some kind of error about we cannot play this video in your browser. So there's some video it can't play, which is kind of weird. So, but this is JSON, right? Like this is the standard thing in the web, and in Bitcoin, it's the same idea, but you're doing it with bytes instead of JSON, raw bytes, right? Because TCP sends bytes. It doesn't send JSON. It sends bytes. And so a stream of bytes. And so that's what we've been doing, right? We've been reading bytes and turning them into Python objects. So here we're going to do the opposite. We're going to take a Python object, right? We're going to take this version message. We want to figure out how to turn this from a Python version message into bytes. So basically the opposite, right? Like we're going to want to do this. We're going to want to do def 2 bytes. Right? We're gonna want to start with something in Python and turn it into bytes. So I'm kind of repeating myself here, but it's just the exact opposite of what we did last time. So that's a lot of information. Any questions about any of that?
No, I don't think so. Sounds good.
Cool. And John, if you're lost at all since you missed some of the last lessons, I apologize. But you know, pick up what you can and all.
I've been watching some of those videos, so
okay, that's good.
Yeah, I'm not getting 100%, but I'm following along.
Okay, cool. Yeah, nice. And so, I just want to make sure I'm actually recording here. I'm always terrified. It says I'm recording. Okay. I'm always terrified I'm not recording. Okay, so
that's one quick question, Justin.
Yep.
So you would call it a Python object, would you? Because it's not JSON.
No. So this is a Python. Like when we say, let's see. This is a Python object, right? When we say, like this is the last thing in the last lesson, right? We read one of these packets, which is the same thing as message, right? I just renamed message to packet because now we have version message. So I thought that was kind of confusing to have message and version message. So you read a packet, right? And so now this is a Python object. This is just a Python thing, just like the number 1 in Python. Like this is a Python object, and that's a Python object. So is this. It's just it's a thing in Python, and then we read this specific version message, and that's also a Python object. Does that make sense? That's what I mean by Python object.
And a collection of objects would also be an object?
Yeah, exactly. Because basically anything like, right, this, even socket, right? Like, you know, like we import socket, right? It is actually a module type object. You know, peer IP. Sorry. So peer IP is going to be just like a string, right? You know, but it's actually it's a string type object. And so, in Python, like everything's an object, but the statement here, import string, that's actually not an object anymore. That's like an expression, I think you'd call it. Either expression or statement, I forget which one. Or this like peer IP equals thing, that's not an object. That's an expression, I think. Expression or statement, I forget. But it's like a compound. And so every like individual thing is like, for example, sock.send. I guess that's still technically an object. It's a function, I think. I don't know if you count like a method as an object. I'm not sure. That's a good. Is a Python. I'm guessing it's not. See, this is what you do when you program your. Yeah, I guess they are. Yeah, so I mean, it's still an object, technically. Sorry, that's just a little interlude there. Yeah, any other questions? Does that make sense?
Mm-hmm. Thanks. And
so the reason why this is so important, right, is like our peer is like 99% of the time, 99% of the time, didn't I just 99% of the time our peer is going to be one of these guys, right? These guys have no, I mean, I guess technically they do have Python. Usually they do have Python installed because the test code for Bitcoin Core is written in Python. If you go to this test directory, which I actually recommend, you can learn quite a bit by reading some of the code here. They probably, some of them probably have Python installed, but I bet there are nodes where they don't install Python on the, the server that's running the full node. It doesn't even have Python installed. So like we can't send them some Python specific thing. They're not going to understand it, right? There's C++. This is like,
so the only Python in Bitcoin Core is tests.
Yeah, exactly. So, if someone's, has a node that they also like develop on and run the tests, then they'll probably have Python installed. But like, if it's just a full node, I bet a lot of them don't even have Python. Some of them probably don't even have Python installed. Though that's kind of changed. Python's so popular now that like most distributions have it installed, I think. But like you can't even guarantee that they'll have any idea what you're talking about if you send them anything Python related, right? And the same thing with kind of C++. Like the protocol could send some sort of C++ specific thing back and forth. Then that sucks, right? Then you can't write. Then that would make this impossible, right? Here's BTCD. This is a Go implementation, 99% Go of Bitcoin Core. And then what is it, Bcoin? Here's an actual JavaScript implementation that's pretty damn good. 99.7% JavaScript. I was reading this the other day. I mean, this is like a very mature project. And like these are full nodes that are not in C++. And so that's the beauty of having serialization, meaning like turning all your data into like a neutral format that everyone can understand, like JSON on the web or bytes on the Bitcoin protocol. Is you can write clients in all these different languages, right? If it was C++ specific, we wouldn't be able to write our little Python client here. So that's the beauty of it. Making sense?
Yeah.
Yeah, totally.
It's interesting to see some of those other languages too. There's some C in there, and what was the other?
Can you see your faces here? No. Okay, never mind. I was trying to see if I could get the faces into the window, but I don't know how to do that. Okay. So we're going to do kind of a new thing here. Like I've been learning a little bit more about Jupyter. Like what you really want to do at the beginning is import everything you need. And then so you don't want to be importing at the beginning of every cell. So like these are the main things we're using now. And it's pretty cool that the list is so short. Like I deleted, we used to use this IP address thing, and we used to use date time, but I managed to remove those. So it's pretty cool that we're getting this far without, I mean, and these are the only ones that do anything. Like these two are for tests, for my little exercises. So it's pretty cool that we're getting so far with so few dependencies. And this one just makes, it's just like an IPython thing that'll allow us to edit some, you can edit like a file. For example, this is like the complete code from this lesson. You can go and edit this file and then re-import it, and you'll get the newest version if you have this thing, this auto reload thing installed. So just execute that cell, and then you're kind of set up. So this is what we want to do. We want to have, this is like kind of hard to read, I guess. But this is kind of what we want to be able to do in our code. We want to be able to say, we want to be able to go here, see where my cursor is. It's like we're creating a version message object, right? And we're just passing into it whatever the hell we want, right? And there's actually some errors there. But yeah, so we want to be able to, you know, say what, these are the, remember services, that was that bit field thing that we were dealing with. So this is just the first, this is just a node network bit, the most basic bit, none of the newer things. Here we can say whatever user agent we want. You can say what start height. So this is important because like they'll know if you've done initial block download or not. You can do all these, you want to be able to say whatever you know, what version you're on. Are you on a, can you understand all the new things that are in Bitcoin, or are you on some old version? And so we want to be able to say the, you know, put in any parameter we want, right? And then basically this, sorry, it's annoying if you click on it, it goes into edit mode. This here, we're just taking the version message and turning it into a packet, right? We're taking the command from the version message here, command equals version message.command. And if you kind of remember how it did, this is so annoying. Where is it? Yeah, so you remember at the beginning of everything, we had this like class level parameter here with the command. So it's just like, you know, we're gonna have a lot of these. So every one of them, we're just gonna say what the command is in the, and so then you can access it to your version message.command, right? And then payload is version message.2bytes. So this is not implemented yet. This is the magic thing I was saying, like, remember here, if we could do like a 2 bytes, that would be great, because then we'd be able to take this version message, turn it into a packet, and then we'd be able to say packet.2bytes. And actually, when we do that, that's something we can send over the socket. Remember just how we kind of the same exact thing. Remember how we read from the socket with this is now called packet. We read from the socket here. We will also be able to, I mean, it's the opposite operation would be like packet dot, or, you know, how do we say this? This is just the inverse operation. This goes, you know, bytes to packet. This goes packet to bytes. So that's what we want to be able to do, and then we can send it. And so this is how we're going to be doing a lot of this. We're taking a Python object, kind of a message object, putting in the parameters we want, turning it into a packet, and sending it. So that's what we want to do. And the two things that are missing are version message.2bytes and packet.2bytes. So serialization, we don't have any serialization yet. So any questions there?
No.
What is serialization?
Serialization is, there's a link up here somewhere. Where is it? Or did I not add the link? Oh, here it is. No. Oh, I thought I made a link. Serialization is, let's just look at the Wikipedia. They had a good.
So you explained deserialization as converting a Python object to bytes. So it'd be the opposite direction, right?
Yep.
From a bytes to Python object.
No, deserialization is from bytes to Python object. So how would what's the best way to like?
Is it you're turning the data into neutral data, kind of like
Serialization? Yeah, that's what serialization is you're turning your
okay.
Python specific thing to neutral thing.
So when you're receiving information, you're deserializing it.
Yes.
Okay. Okay, I somewhat follow along with that concept.
Yeah, so like think of like, I don't know why they use the word serial. I mean, I think it might be because like it's a series of bytes, maybe. Like it's probably something along those lines.
Could I see an example of serialized data?
Yeah. So the beginning of, remember this is
okay.
This is serialized data. See, it just starts with a B, and it's just bytes. That's generally the stuff in this, not always, but generally anything that starts with it's a byte string. These are, so this is also serialized. So like in the first lesson, I just give you, first and second lesson, I just give you this version thing, right? And then we say version sock.send a version. So this is all we're replacing. Like that big chunk of code I just give you, like this whole thing here would be equivalent to just this one line. But the problem with this one line is it's hard coded and we can't change any of the parameters, right? Like the only thing you can see here is the user agent. It's just some cool software. God, this is so annoying when I click it, like some cool software, right? You can see that, but you can't change it. You can't change anything here. You can't change the version number is stuck in here somewhere. The services thing is stuck in here. And so, yeah, to repeat, this whole chunk, all these lines, just make one of these, but they make it however we want it. That makes sense?
Yeah,
Yep. So this is serialized, and anything in Python like this is like is deserialized. So, for example, this is unserialized. This is Python, right? This would be the serialized like version message payload, message at 2 bytes. This is now serialized, and this would be the serialized entire packet, right? And so the packet, remember, just adds these things on the outside, right? Like it would start with the magic number, then it would have the command, then it would have the payload length, then it would have the checksum, and then it would have the payload, right? So this payload would be what we get from saying version message.2 bytes. This just creates a payload. So we could actually rename that to something like 2payload or something. But yeah, so there's a lot of description here, and I think I've kind of gone over everything here. Yeah, we want to make some methods some 2 bytes method that serialize our data. So the first thing is I'm just going to make a simplified example to kind of give you the idea what's going on. So let's pretend the Bitcoin message has a pet data type, right? So for example, these are all the things that Bitcoin has, right? Let's just say like 3.0 here. Just imagine if it was pet. Like there was something about, this is a really stupid example, I know, but like let's just pretend there was a pet. Just similar to net adder or services or something. And this is what the table would look like, right? Like remember how we had, we have these tables, field size, description, data type, comments. Let's just have the same thing here. So field size, the first field would be 3, right? Sorry, bug. That should be 1. Okay. The first field size is 3. This is the kind of pet it is, and it's just char of 3, so it's a 3-character byte string. And then here are the valid options: dog, cat, cow, or pig. Right? I know, it's stupid, but and then the next one is name. So it's a 10-character field that's just the pet's name, right? And so this is what the class would look like. You'd have class pet. Maybe you'd have this valid kinds here. You could say like, so, you know, there's the class itself has two attributes, kind and pet. And just like before, we have from bytes, right? So you could have like a byte representation of this pet that you could send over the network and you'd read it, right? So the first thing is you'd read 3 bytes and you just leave them as how they were because it's not an int or anything. We just leave them as a byte string. And then the next would be 10 bytes. And maybe you could have something here like if kind not in I don't know, something like this, like when you read the kind, check if it's one of these ones, you know? Like let's not have any other type of pet that's valid. This is stupid, I know, but you get the idea. This is deserialization. So let's try to write 2 bytes. Let's try to, you know, if we have something like this, name is equal to, what should we, Rover? Let's name, so we have a dog that's named Rover, right? So how can we turn this into something that's like this? You know, or, you know, remember how previously it was like, you know, how do we do something like this? You know? And so that would be like a 2 bytes method, right? Let's just turn it into a serialized byte string. And so I'm going to try to get you guys to write this method. And there's just one little test for it. So let's say this is what the serialized thing looks like. This is almost too simple, but so this is what it would look like serialized over the network. And so you could send this over a socket, right? And so what we want our 2 bytes to do is like, here's what we're doing. So if we're saying from bytes and then 2 bytes again, basically if you go all the way around, if you deserialize and then serialize again, you should end up with what you started with, right? So here's the message, right? Pig buddy, right? So this is a pig named Buddy. If you do this, if you turn it into a pet object, you go from bytes of pig buddy, you'll turn it into a, you know, it'll look like this. It'll be the same as this. And then if you do 2 bytes again, it will go back to pig buddy, right? So that's what I'm asserting is like, hey, if you pig buddy pet bytes will be equal to the same thing as if you do from bytes and then 2 bytes again. And so this seems kind of stupid, but we're going to be doing a lot of this type of thing when we're dealing with blocks and transactions and stuff. So yeah, I want you, so you trust me here, if we try to run this test, what the hell? Test pet 2 bytes. That's interesting. These are test cases for, sorry, I think I failed to clean up a test elsewhere. Okay, I'm gonna have to restart this just because, so this is just from me, I was editing this stuff before the class started, so I think if I restart everything here, that should go away. Okay, good, sorry. That was just, that's a test we're gonna run later on. This little test thing, you have to clean up the tests, and I forgot to. So, so yeah, see how this test fails? Oops. What the hell?
I'm getting that error as well right now.
Which one?
Oh, I'm getting name error that IPY test not defined.
Wait, who is this?
This is Chandler.
Oh shit! I didn't know you
Yeah.
were on.
Oh yeah, I'm not on a computer with a webcam, so I'm just audio here.
Oh, okay. Sorry, I just see the thing of faces, and And so
No
I
worries.
forgot that you exist. I didn't see you. Okay, cool. So what is the name of the error?
Oh, sorry. I'm actually getting a name error that IPY test is not, IPy test is not defined.
Okay, did you execute this first cell with everything in it?
Wow. Derp. No, I did. Let's see. That's probably what it is. Yeah, that did it.
Okay, cool. So everyone should be getting a not implemented error, right? Like that's what in Python you can like define a method. It's just a note to yourself, hey, we want to implement this, but we haven't done it yet. And so any code that tries to use it will blow up. So I want you guys to make this test pass. There's a one-line thing you can put here that will make this test pass. Okay, does that make sense?
Yep.
So I want you to serialize pets. Okay? You'll be a Bitcoin engineer soon, I promise. All right. I'll be right back. I'm going to get a little coffee here, but I'll give you a minute or so and try to see if you can kind of figure out what's going on here. Okay, anybody got it? A little more time?
I'm getting a weird error, an indentation error. I don't know why I'm getting that error.
Okay, if you Slack it to me, just the error. How are you doing, Gustavo?
I'm fine. I managed to do it. Just
You
concat.
managed to do it?
Yeah, just concat, right? The kind and the name.
Yeah, that's it's. John, did it make sense at all to you?
No, I'm gonna have to. I'm having a problem with Jupyter. I can't see the. I can't see the file that you have on your screen.
You don't? Okay. Git pull.
Okay.
Git pull. So have you made any edits to? Yeah, if you've made any edits to any of the things, like made little notes or anything, they'll probably get blown away. But I think that's probably fine.
I don't think I have anything too important, Justin. So.
Yeah. So yeah, git pull, and if you have any merge conflict, I'll tell you how to fix that. But git pull. So I just uploaded these like half hour ago or an hour ago.
Yeah,
Okay.
I've been getting my git pulls. If I've modified things, it'll fail and say you need to like check out or merge.
So
but I just had to copy them out, copy them out or delete them, and then they get recreated. But it blows the changes away.
I need to figure out a better way to do that. That's like the one really annoying thing about Jupyter Notebooks is they're just big JSON files, so they're very hard to. It's very hard to like keep your own changes.
Yeah, but just copying them out and then like just for the old lessons, copying them back in if you want to keep them. It's not that hard, but it's a pain to do it every time.
So Michael, if you, yeah, exactly. Yeah, that's good. That's probably the best thing to do. Yeah, do it. See, Gustavo just put something. That's probably the best thing you want to do is just, it'll just reset
Yeah, thanks,
whatever
Gustavo.
the remote thing is.
Oh, I have to ask a beginner question. What do I need to put into the terminal first before I put
So you
that
just
in?
need to CD to wherever your Bitcoin, wherever this code is. So wherever where you ran Jupyter Notebook, wherever you ran that, you need to just get to where that is. So you do CD and then like something/something to wherever that location is.
All right.
That makes sense?
Working on it.
Okay. So Michael, what happens if you delete that line that says not implemented, raise not implemented error, and just say like, print hello? Does the error go away?
How do you see the line number?
So it should just be in the class pet, that cell where it says, it says this line here. What happens because it looks like that's what, like I'm guessing that you have it's like this or something. You have it like 3 spaces because in Python you have meaningful white space. So like it has to be like 4 spaces to be indented properly. It has to be some multiple of 4 spaces. So I'm guessing there's something like that here where there's like an extra space. So what happens if you just delete that and just say, like print foo or something, and then run the 2 cells? Oh, that's weird. What? All right. Well, this one, I think, Michael, this error will go away. So I'll just show you guys what the answer is. So we just want to kind of do the opposite of what we did up here, right? So the first thing we did when we read the thing was we read the kind, right? Kind comes first. So that's what we'll do. We'll return kind, self.kind, and then what did the second thing we read? The second thing we read was name. And so we just do self.name. So we're just concatenating these byte strings into one longer string. And I think this should pass. Yeah, so the test passed. So all you got to do is kind of concatenate these 2 strings. And it's really simple in this example, and that's why I like this example. And so when we get a little further along, we're going to be doing it with, this looks fancier, but it's the same idea, right? This looks fancier, but it's the exact same idea. You're just going field by field and adding these byte strings into one big byte string. That makes sense?
Yeah.
So hopefully that embarrassingly stupid example helped. Okay, so this one, I think I need to delete this little thing. Okay, so now let's do it for real. Like let's not do it for pretend anymore. Let's do it for real. So what we want to be able to do is we want to be able to have packet.toByte. We want to be able to turn a version into bytes. We want to turn this version message into bytes, and then we want to turn it into a packet, and then turn that into bytes. So it's a little convoluted, and maybe in a future version of this, I'll make this code a little simpler. But I think it's verbose. It tells you what we're doing here. So let's start at the outermost layer of the onion with packet. Let's figure out how to make a packet message into bytes, a packet Python object into bytes. And so I'm just going to show, like I kind of I think in a future version I should make this an exercise, but I just kind of with these longer ones, I'm just going to show you how they work. And maybe in the future, I'll turn them into exercises. So this is the same. I mean, if you look at this, this is almost exactly the same as what we made at the end of the first class, right? Read from socket, you know, now we call it just from socket, you know, command, payload. It's about the same exact thing. But we just made 2 bytes here. And so 2 bytes, it's the same ideas, right? You start with some byte thing, and then we're just going to add every attribute onto it. So plus equals is just say, like, we'll start with what result, and we'll just add a little more to it. So it's a way to build up this result as we go. And so the first thing is you do int to bytes of network magic, right? So let's pull the version. Well, let's pull this up. Right, so we're just going to go field by field. So the first thing is 4-byte network magic, and it's an int, right? So if we go back, we're going to write the network magic, right? And that's it's actually not. Let me think. We should. It works because I imported it, but here I'll just copy it from the file where it's actually defined. So let's just put this at the top here. So there's network magic. It's just a hex number. This is just like the magic number in Python or in Bitcoin, remember? So here it is, 0x D9 yada 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 yada. And so D9 yada 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 yada. And so that's what we do. The first thing, field size is 4, and it's an int. So that's what we do. We do int to bytes, the thing we want to do, and then 4, right? So we're just writing the network magic onto this string, right? And so here's int to bytes. It's, you know, we did a lot of this bytes to int, and this is just the opposite. It just turns an int into bytes with a certain number of bytes in a certain byte order. That make sense?
Yep.
Cool. And then, so the next, was that something else?
No, it makes sense.
Okay, cool. And then now we just go down, okay, what's next in the list here? Command, all right. 12 bytes, and it's just a char, just characters, a string. So let's do that. We have, we just do this little encode command thing. This is ugly, like in the future, this should be simplified, but if you remember how this works, like, at the top, we don't have a bunch of like, when you see these in a real message, what's a good example? See how it's like version? This is a real one, version, and there's a bunch of these X zeros at the end. You see that? So since this is a 12-byte value, they pad them to the right until it gets 12 bytes, right? So version is 7 bytes long. There's 7 letters in version. And then see how there's 5 of these X00, so you get to 12 bytes, right? So that's how these work, is they write padded with these X00 empty bytes. And so when we have something like this that's just version, when we encode it, you know, we don't have it like, we could have it like this, you know, or let's just say plus, like we could do it like this, you know, version, and then like let's write pad it with 5 of these bytes, empty bytes. Does that make sense? So
Yep.
it would look
Yeah.
like this, you know, but that's kind of ugly. So like, let's not do that. Let's just leave it version. But then when we send it over the network, we got to make it look like this, write pad with however many bytes until it's 12 total. And so that's what this encode command does. All it does is it says, okay, how much padding do we need, right? Like basically 12 minus the length of the command, right? So in our version example, the command is 7 letters. So len of command is 7. 12 minus 7 is 5. So let's just make 5 of these empty bytes, and let's just put them on the right side of command, right? So, I mean, that's basically what we were doing here, right? Let's just take 5 empty bytes, put them on the right side. And then, so then that's ready to go on over the network, right? Does that make sense? Any questions on that? I think that's kind of a confusing thing. So hopefully I explained it well enough.
What do you think it's confusing? Do you mean the latter part or the whole thing?
Well, it's just kind of weird. You're just like adding bytes around, and it just seems sort of a stupid thing to do. But yeah,
I get the padding concept.
Yeah. Okay. Cool.
If you've said it needs to be a certain size, it needs to be a certain size.
Yeah. Exactly. That's what I'm trying to say. Is
even
like
if you don't need,
it's got to be the right, because if you forget to do that, then when you're reading it, right, we're going to read the command, and remember, read command will read 12 bytes every time. So this isn't, if we mess up and only put 7 bytes here, it's going to throw off everything, right? You got to always have these things be exactly the right length, or else it just throws off everything, right? So if this reads 12 and we only put 7 in there, then the last 5 bytes they're reading are going to be part of the payload length. So you'll get them off a little bit, and then your entire program is worthless. So yeah, that's the next thing we do. And then we do int to bytes of self payload, length of the payload. So this is just this step, right? You have a payload length, 4 bytes integer. And so that's all we're doing here is like, let's just take the length of the payload and let's make that into a 4-byte integer. So that's pretty straightforward. I mean, it's the same thing we did in this first line here, actually. And then lastly, we do compute checksum. So if it's going to be hard to, well, I guess it was here now. Yeah, so we called it calculate checksum. So you remember this is we just do this SHA-256 twice, and then take the first 4 bytes. Just roughly to bring this back in your mind. And so remember when we were reading messages, that's what we had to do first, right? Is we were, when we're reading messages, we were calculating the checksum on the payload we received, right? And then we were checking it with the checksum they gave us, right? And so now, again, we're kind of doing the opposite. We're going to write in this checksum for the payload we're sending so that our peer can check it with their own, so that they can, run a checksum on the payload and see if it agrees with what we tell them our checksum was. Does that make sense?
Mm-hmm.
And again, this is just a precaution to check that no bytes were kind of lost or dropped in the transmission of the packet. And so lastly, we just tack on the payload, right? And the payload can be arbitrary length. It can be however long we want it to be. And the reason why that still works is that we put in the length of the payload so that our peer knows how many bytes to read to get the payload. So does that make sense?
Yeah, I have a question.
Yeah.
So why can't they all be of arbitrary size up to, like, say, a maximum? Would that be more efficient rather than just sending a bunch of...
Yeah, I think, I mean, in some cases it could because, well, I mean, in a lot of, the thing is a lot of times they don't vary very much, right? Like you could have an arbitrary length command, but I mean, they're already like, they're almost all like they're from 3 to 11, I think, so they don't vary too much. And so there's an overhead, when you have a variable length command, there's an overhead in that you have to, in front of every command, you have to say how many bytes is going to follow. Remember when we were doing, yeah, here it is, read var int. Remember when we were doing this? The first byte the first couple bytes would always be the length of it would be the length of the bytes that followed. So there's like an overhead to making variable length, and with a lot of them, the checksum's always going to be 4. I mean, the payload length could vary a little more. Like usually, it's for a block, it's going to be like a 2 or 3 byte integer. For a lot of times it's going to be, or maybe bigger than that. A lot of the times it's going to be less.
The checksum is obviously always going to be 4, but there was a lot of padding there that we saw, and I just wondered, like, obviously the overhead for declaring how many bytes it's going to be, isn't
Yeah, I mean,
isn't anywhere near as big as all that padding that we saw in that example.
Yeah, it's a bigger stuff like that's a bigger deal when you're talking about blocks. Like if you zoom out, I mean, almost all the difficult stuff in Bit, like all of the work is done on decoding these, right? Like this is where you get an arbitrary number of transactions, and this is going to be like a megabyte every time, or like it can be up to a megabyte every time. So like this is where all the work happens in Bitcoin. And a lot of the other stuff, it just doesn't really matter too much. And so as you see, like the important stuff, like this is variable length. It first is how many of them there are, and then it's the transactions themselves. So I think you'll see that whenever there's something where it's actually important, they usually do have a variable length. But like having an extra 5 empty bytes in general is like dust. You know, it just doesn't matter.
So just to clarify, like if the payload length only takes 1 byte to express because that's small of an integer, do you pad the other remaining bytes as well to the to the right?
Yeah, so you actually do, and that's the little endian encoding. Remember when we were doing let's see.
That's right. That makes sense.
Yeah, well, let's just do an example. So if we execute this cell up here, right? So now here you have int 2 bytes, and you can just execute to see if, what the hell? Oh, that's weird.
You're happy with little endian? Sorry, I don't know who was speaking last.
Oh, that's weird. Look at this is like an IPython bug, I think. So when you execute this, it has like something can't print this when we just print the function, but when we call it, let's say we're encoding 1 as a 4-byte. It's 4 bytes. Oh, look at this. This is weird. Shell.user ns. That is weird. Well, let's just try. I'm just going to go back and try this. This is like something is wrong with IPython right now in my setup. I broke something. So let's just say 4 byte order little, oops, and 1. So this is like how it actually works. Oh, wow. Okay, I'm just going to restart my IPython because something's clearly broken. I wonder what that is. Okay, there we go. So you see it does write pad with, when we do it with, well, let's do it for real. So yeah, so into bytes of, let's encode the number 1 and let's make it a 4-byte integer, right? So little endian, so the most significant digit starts on the left. So the most significant digit here, or the least significant digit starts on the left. And so these are like the bigger digits, right? Like these are the, these are like thousands and millions and stuff, right? And so that's all 0, right? So it's filling in, it's padding all this stuff. And if you do, if we tried a big endian here, big. If we tried a big endian here, see how it goes backwards, right? So then all of a sudden the least significant is on the right. So big endian is like how normal numbers we think of them as, is like the least significant is on the right. And so yeah, that's your answer is, this always produces an output of the same length.
Yeah, okay. That really makes sense.
Cool, it's a good question though. But yeah, and I mean, I'm sort of trying to, in the future, you're going to, like, I have had developing the state kind of like trying to do the initial block download or like a crawler that crawls. Like that's what next lesson is. We're going to make a crawler that can crawl the network and download, try to connect to every single peer. and download their version message and kind of see a little bit about them. You're going to have a bug every once in a while where you like read 4 bytes instead of 8. And then all of a sudden, like, half of your message will make sense. And all of a sudden, wherever the bug is, the rest of the message, all the data is senseless. Like the timestamp will be like a timestamp from the year 3000 or something. It just gets completely messed up. And so you got to be really careful about always reading and writing the right number of bytes. So does that all make sense? That ready to move on to the next one?
Yep.
Okay, cool. And so, yeah, so we started with the outermost layer of the onion, right? We were starting with this packet.2 bytes, right? So now let's go inside the onion one more layer. Let's try to do version message.2 bytes so we can fill in the packet's payload attribute. All right, so we're kind of going into the onion, right? We started out here with like packet.2 bytes, and now let's go inside with version.2 bytes. So here we are. Here's version message. Everything up here above 2 bytes is the same as last time. And sorry, now this is getting so long that you can't all see it on one screen, which sucks. Well, let's fix that. So just as a hack to make it easier, you can just delete this and stick it up here, I think. I don't think this should break. Okay, there you go. You can kind of see it a little better. So here's 2 bytes and for version. And now this is getting even more complicated, right? Because version message, if you remember, has kind of more stuff going on than packet does, right? Remember, there were adders, and there were the services, and there were the timestamps, and there were booleans, and there were all kinds of crap going on in here. And so this is what the code will look like. And again, I don't think we maybe need to go through every single thing, but it's exactly the same thing, right? You just go over to, you just go down this list and write these things as you go. It's like the first thing, int to bytes of version, right? And then the next one is services to bytes of services. That's that. It was a dictionary. I just actually, yeah, it was that dictionary, node network, node bloom, all those things. Here's time to bytes of time. And so this one's a little goofy because if you look in some of these things, like for example here, the timestamp is 8 bytes. But if we want like a general, so here you go. In block, timestamp is 4 bytes. So it's tricky. Like there's not a standard way to write timestamps. We're not going to be able to write like one function that just always does it. And this is a bug. Like Satoshi messed up here. Like for example, yeah, these will overflow in 100 years, less than 100 years. The timestamp won't be able to fit in 4 bytes anymore. And so here, all of a sudden, he has an 8 byte. So this will never overflow. And so it's weird. Like he clearly made an error making some timestamps one length and the rest another length, right? And so yeah, this is a huge bug. And it's a bug that's still unfixed and probably won't be fixed for decades, because there's no urgent need to fix it. But so it's kind of annoying whenever we read timestamps now, we have to say how many bytes it is because Satoshi messed up, because he had 4 bytes in some places and 8 bytes in others. But for the version message, it's 8 bytes. And so here we go. Look at this. So for version message, remember we have this adder from, adder receive. And adder from and adder receive is actually like, if you remember, it's actually a class, right? And so the onion actually goes one layer deeper. We're going to need to implement this. We're also going to need address.2 bytes, right? Because in order to serialize a packet, remember, in order to serialize a packet, we need the payload, so we need to be able to serialize the version message. Well, in order to serialize the version message, we need to be able to serialize adder receive and adder from. Remember these two? Yeah, these two, adder receive and adder from. And so these are a Python class, and so we'll need to implement a method to do that. So here you go. The onion is now 3 layers deep. And so this is kind of like, we haven't done that yet. And then, so there's 2 of those addresses. And then into bytes of the nonce. Nonce is just a random number. Stir to var stir. So this is the hard one that we're going to have to implement. We're going to have to be able to write a string to a variable length string. And we do that with the user agent. Remember this, the user agent, just so we don't get lost here. Yeah, so the user agent here, var stir, variable length string. Yeah, so remember this one? At the beginning, there's a var int of how long it is, and then it's the string. And then var int was the one with all this goofy shit going on. When you look at the first byte, you see based on how big it is, how many bytes come afterwards. So in order for us to do this stir to var stir, we're also going to need to implement int to var int, right? Because var stir has a var int inside it. So this is going to be some work we're going to need to do. And then int to bytes of the start height, and then bool to bytes of relay, and then boom, we're done. And so here are a couple methods we still need to implement. I did time to bytes for you because it's basically just int to bytes now. And so here are 2 that we're going to have to implement: bool to bytes and stir to var. Wait. Yeah, and stir to var stir. Does that make sense?
Yeah.
It's the same exact thing as what we were doing with pet. And like, I'd encourage you to go through and play with it. Like, I should have made this an exercise, but I'd had to write a lot of tests for it to make it so you could kind of understand if you're on the right track. And it's just too much work for the first time around. But it is the exact same thing as what we're doing here. It's a little more complicated. But in concept, it's the same thing. We're just adding bytes and then returning them. And so let's do this. Here's an exercise. Let's implement bool to bytes. So here's bool to bytes. Remember, Boolean is true or false in Python, right? And so I want you to turn this into bytes, into a byte representation that we could send over the internet. And so just as a little hint, what you want to do is you want to interpret the argument B as a bool, so you can do like bool to turn, you can do that to turn something that isn't a Boolean into a Boolean. And then last time we did this int to bytes, and so that'll turn ignore what I just said. You start with a Boolean and you want to turn it into an integer, right? And so you can use int. And then we have this thing called int to bytes. And so once we turn the Boolean into an integer, then we can turn that integer into bytes. And you want it to be 1 byte long. So it's almost more words than it's a lot of words to explain. The code is really simple when you figure it out. So try to implement that. You'll see the test fail now. Try to implement that.
There's a question on the timestamp, Justin. It would be better practice isn't it best practice to have as few global variables as possible? So you would still, if you're applying best practice, declare the timestamp variable locally each time rather than having it as a global variable.
Yeah, where are you talking about?
We were just discussing the timestamp earlier in the Satoshi slip.
Oh yeah, exactly. I don't know why he had that bug. Like, yeah, for example, if he would have just had like an address class, or yeah, if he would have just had like some, if he would have just written this once, if he would have just had a function like this, basically, that always wrote the same, where this was full, like 8 or something, or like even 6, you know, six is not going to overflow. 6, if you would have just had something like this where anytime he wrote one of these, it would have wrote the same. Yeah, he wouldn't have had this bug. Like, this is a bug because he probably wrote the same code, you know, separately in 2 different places. So yeah, he probably had too many global variables. That makes sense?
Yeah, I'm just trying to work out. So like, yeah, like timestamp. Ideally, timestamp wouldn't be a global variable. Is that correct?
I don't know in what sense you mean it.
It doesn't matter. I'll look into it.
Yeah, I mean, yeah. Okay, well, let's try this one. And so, yeah, if you look at the test, you can also cheat and see what the answer should be in the various cases, right? Like, in the case of true, this is what you want it to look like. You could hard code it if you want to pass my test and be a bastard about it. Okay, how are we doing? Anybody need a little more time or no?
I'm good.
Okay. Michael, John, making progress, making sense?
Somewhat.
Okay. Ready for me to show the answer? A little more time?
Yeah, go for it, Justin.
Okay, so, okay, I'll just do it step by step. So B here is a Boolean, right? It's true or false, right? So let's turn it into I for integer. So I is equal to int of B. Okay, boom. So we turned it into, so now this is, sorry, I was writing C++. So now it's a 0 or a 1, right? And so next what we want to do is we want to just call into bytes of I and a 1, because it's just a 1. We look at the protocol documentation. This bool is used for relay, and it's just going to be, it's always just going to be 1 because it's just a 0, you know, number 0 or 1. So even a byte is like a lot of space, right? Because a byte can store 256 different values, and this is just, we just need 2 different values, 0 or 1. So I mean, we could store this in a bit, right? This is not like, we only need a bit of information to store a Boolean, right? That's the definition of a Boolean. It's a 0 or 1. So yeah, so that's how you do it. You just turn it into an int, and then turn that int into a little endian encoded 1 byte byte of one length. So there you go. Test passed, right? So in the case that it's true, you get this, x01. And then in the case that it's false, you get the null bit, this x00, which we see a lot of this guy, right? We see him all over the place. This is Satoshi's favorite bit. Okay, so now let's do, wait, what? Test, sorry, little test bool. Just wrong name for my test here. You can see I copy and paste a lot when I write these. Okay, so now this is like the hard part of the lesson. Basically, the rest of the lesson is pretty simple. This is like the hard part, or like the challenging part. So now, see, we wrote bool to bytes, and that was needed for a relay, to encode a relay, right? And now for user agent, we need to do the hard one. We need to do var stir, right? So here's stir to var stir. And if you remember, you know, var stir is one var int, and then that, you know, that many characters afterward. So we also have to implement var int. And so I think I probably made a, let's see. Yeah, so now we're down here. So if you look, we have to, in order to do var stir, we got to implement var int first. So I gave you a link reference here. So I want you to make this test pass. See, I'll convince you that the test doesn't pass. Yeah, I mean, it's just so there's not a, yeah, so get rid of all the fix me's and make this test pass. And so, I don't know, if you want to look for a little inspiration, remember we did do something, we did do a test kind of similar to this. I think it was in here, wasn't it? I think somewhere in here we did something like this. Yeah, so if you look in the middle of lesson 2, remember how we had this, you know, this test that was similar about reading of var int? I guess you've now all deleted your solution there. But so maybe, so that might not actually help. But I mean, you should be able to figure it out from the reference, right? So like, in the case that the number we're trying to encode, right, is less, this is like 254 or something, right? If it's less than this, just turn it into bytes. Turn it into, so like, let's just do it. So like, let's say I is 17, right? And then so I less than, so we're gonna see it is less than that. And so then this first block will hit. And so let's just turn it into, let's just I'll show you. So this will turn it into one of those like raw bytes, okay? So it is less than 0xFD. And so this is the hex representation of 17, right? Which makes sense, right? There's one 16th place and one ones place, right? It's 16 plus 1 is 17. And so that's good. And so then, so does that make sense? In the case that it's a small number, this is what we do. Have I lost anybody?
I'm good.
Right, because if you remember this chart, right? So if the value of the variable length integer we're trying to encode is less than this, right? It's like 254 or something. Then just the variable length integer is just, or the variable length integer is just that thing. You don't have anything else, right? But if it's more than 0xFD but less, basically if you can fit it into 1 byte, then just let that byte represent the number, right? But if you can fit it into 2 bytes, right? So this is, each one of these each FF is like, 256 possibilities. So like if you can fit it into 2 bytes, then let's say that the 0xFD, because that's basically what it's going to be. So if it's less than 0xFD, or if it's not less than that, but it's less than 1 greater, yeah. Sorry, this is like slightly confusing, but this chart here. But basically, if it's a little bigger, then you interpret the next 2 as a 2-byte integer. If it's a little bigger, you do the next 4 as an integer, and if it's bigger than that, you do the next 8 as an integer. So that's roughly what we're trying to do. And so, so yeah, this is it. This is how it just kind of works. Is you like, the second row corresponds to this block in the if statement. Sorry. So yeah, just try to. I didn't explain that very well, but try to see if you can fill some of this in and at least get some of these assertions passing. And so just as like a hint. So there's kind of a hint. Okay, see you, Michael. Is Gustavo still here?
Yep.
Oh, okay.
I didn't get the last value because you have an else if and you still right.
Mm-hmm.
Just you have like the last else if that has a fixed me.
Yeah.
Well, from the table, it's not that right because it's done with the dash.
Yeah. So basically, you want it to be. Okay, that's a good question. So I guess I'm gonna.
Oh, okay.
I'm gonna do this. Just like this is a little. So basically, what you want is, yeah, you're checking that it can fit into a 64-bit integer, right? 64-bit, it interprets it as 64 bits. So basically, you want to figure out if this can fit into 8 bytes. And so, I mean,
It's 16 Fs.
Yeah, 16 Fs.
Okay.
Yeah, so that's kind of ridiculous, but yeah, 16 Fs will do it.
And then the other fixed meets like it's the in tool, right?
Huh?
Shit. maintenance function. So the something on your first mix on the return, on your first return that needs to be changed.
Yeah.
It should be something like int to var int, and then you have to see the length of I times 2, I think. So it should be it, right?
So what you actually need with every one of these, the first thing you need is one of these markers. You know, so like, okay, so I'll just start from the top here. So let's do this one. So what we want is int to var int of something. This is the hint I gave you, something, and then 2. And so the way you figure this out is like, okay, if this is true, right, you're going to have 3 total bytes, right? And so the first one is 0xfd, basically, right? Because it's, this is like kind of the marker that says, although that doesn't really, oh yeah. So because when we're reading it, so remember when you're reading it, the first thing you okay, not a very good explanation here, but yeah, so this is like kind of the marker that says it's going to be there's 2 bytes, a 2-byte number follows, right? Remember, because we can't fit it in 1 byte, right? If we can fit it in 1 byte, we do. Our number can't fit it in 1 byte. So what we're going to do is we're going to prepend this marker to our var int. That this means there's 2 bytes afterwards, right? And so we're going to stick int to var int, int to, oh, did I say int to, sorry, that was this. You want int to, and we should maybe stop after this and pick up like tomorrow because I'm starting to get a little tired. Int bytes of I and 2, right? So this is what you want. Int to bytes of I, 2. And I think that's right. That makes sense?
Yeah, that does.
Okay.
Yeah.
Sorry. Yeah, it's not recursive. Sorry about that. And then, so this one, right? So we're basically going to go up 1. So then this one is going to start, right? This is how it's going to start, right? 0xFE. Because that's the marker that says, hey, 4 bytes follow afterwards. So yeah, I just told you 4 bytes. So then what comes next, right?
Yeah, it's 5, so you already have 1, so it needs 4 more.
Yep, it's already got 1, so it needs a couple more, and so that's what the next part will be like. And so yeah, this last one is basically the same thing. So let's say return B. This would be better if, like, so I'm just saying, like, it would be cool if every time we fix one of these, we could go and run the tests and see that it passed. Unfortunately, we just have 1 big test. We should have like 4 little tests. Yeah, so that would be a better thing. It's not like, really when you're writing code, you should, like, if you do one thing, you should run the test and see that it worked. So I mean, we could kind of try that. Yeah, so you can't really see that anything's working here. It's not clear that things are passing. So yeah, the last thing you do is 0xFF plus int 2 bytes of I 8, right? Because that's, remember now it's 9 bytes, 64-bit integer, so it's 8 numbers following it. Oh yeah, that's a good point. And so yeah, I think, I don't know, unless I screwed up. Yeah, so the test passed when you do that. So yeah, it's kind of an ugly function, but like that actually allows you to do this magic of, you know, having a variable length integer. And then if we go to the next thing, any questions there?
No.
Mine failed, but I just want to take a screenshot so I can look at it after this. I don't want to hold it up.
Sure, yeah. I need to make on lesson 2, I had a solutions.py, like a Python file with all the solutions, and this time I didn't manage to do that, but after this I'll make one and upload it.
Okay, I'm good.
Cool. So stir to, and then so the next thing is just stir to var stir. This is a lot easier now that we did the hard part. So remember, stir to var stir, all it has is the first thing is a var stir length, and then after it does you just concat just stick the characters on the end, right? So here is like, so the first thing you got to do is you got to turn s into you got to figure out what the length of s is, and then encode that as a var int. Sorry, encode that as a var int. And then after that, add s, and and then return it. So this is like this could look something like return x plus y, where this is a var stir thing, or a var int thing. Sorry, var int related, and this is s. This is what this one will look like. So why don't you give that a shot?
So it's probably the length of x.
Uh-oh.
Oh. Yeah.
Okay, so this is kind of how it'll work. The first thing you do is you grab the length of s. And even though s is actually, in this case, a byte string, and one of the problems with this course is we're always, like, this function is stupid right now because it's a stir to var stir. S is actually a byte string. Like if, this is actually a shitty job on my part. Like, a lot of times we're passing around these byte strings when we should probably pass around strings. And there's like a little small difference in Python. So yeah, I can improve that. But so that's what you do is you get the length and then you say, okay, int to var int. A length is an int. And so turn it into this var int and then put the string afterwards. And so, yeah, so I have some very large strings here. So yeah, so this is a string with like millions of, probably billions and trillions of digits long. So if you make this much bigger, my computer runs out of memory. So it's kind of stupid, but that's the, so that passes. Any questions there?
No.
Okay, cool. And then, so actually, we'll just try to, okay, so lastly, okay, so this should be an exercise in the future, but I'm just gonna show you how to do it. So, so here's the address. Remember, this is the innermost kind of layer of the onion. And so here is what it is. This is pretty simple. You just, some functions that we've already done. The only complicating part is that basically sometimes if we look up to common structures here and then go to network address, so you have it in bold, not present in the version message. So this time is present in network addresses, but not when they're sent in the version message. So that's confusing as hell. And so this is the only thing is like in version messages, time is not included in the address, which is weird. So basically in our code, we're going to basically say, okay, when we're serializing, we're just going to say, hey, are we serializing this as a version message, right? And we had the same thing in from stream. We said, and from bytes is like, okay, if it's a version message, then we're going to set time to none. Otherwise, we're going to, there's time is there. So it's kind of weird. Like this thing is not always the same depending on the context. And so we just have a little if statement to account for that. And so the only tricky thing here is now we have, you know, we have an IP address. Actually, okay, so I kind of ran out of time here, so I'm not gonna show you how those work today. Yeah, just assume they work. It's kind of like, the only tricky thing is like, let's see. Okay, so this is how this works. So the only thing is this, it's basically an int, right? Because a port is a number. But here, for the first time yet, we have byte order equals big. It's a big endian. And so here's another annoying thing is like, sometimes it's big endian, sometimes it's little endian. This is the first big endian we've encountered. Or, you know, we read this as big endian, now we're writing it as big endian. And so, yeah, that's a little annoying. And then this is, I'm just going to copy and paste it here. So this is how IP to bytes works. Basically, we're going to check if it's IPv6. You know, IPv6 are the ones that are longer. They're like 16-byte addresses. And so we're going to check if there's a colon in it, because colons are in IPv6. They're not in IPv4. IPv4 is just dots. And then we're gonna do some magical thing that handles it for us, basically. And then if it's IPv4, we're going to if it's IPv4, what we're going to do is we're going to format it. But the thing is it's only going to be 4 bytes long. And if you look at the net adder thing, is like, it says, hey, if it's an IPv4 address, you're going to have this chunk that is in front. Basically a bunch of empty bytes and then these 2 full bytes. And then followed by the 4-byte IPv6 address, right? Because IPv6 is just like 4 numbers between 0 and 255, right? So in the case that it's IPv4, we just prepend this, these 10 zeros and these 2 Fs, right? So it's the same as here, right? 10 of these 0 bytes, 2 Fs. So this is just a Python way of saying this. And sorry that you can't see this, but I'll upload this soon, and you'll be able to inspect it. But this is how the ports and the byte stuff work. And yeah, so I'm just going to give this to you, and so now what we'll be able to do is now we can, let's see, let's do this just for good measure. We kind of hack some stuff here. And then we can do, okay, well, look at that. a second. We're gonna do a little bit of this. And okay, that looks like that. Sorry, that's I should have had this prepared ahead of time. So if you look, so now look at that. So we can serialize a version message and print it, and so this is what it looks like. And we can serialize up. We can take that payload, stick it into a packet, right, and then also stick the command into the packet, and then serialize that. And look, well, bam. So now this is something we can use to start our version handshake. That makes sense? That good?
Yep.
Okay. So losing people fast here. His AirPods died. All right. And so we're getting pretty close to the end here. So basically we're done with the version related stuff. Now we're on to Verac. And it's pretty simple. Like, we're just going to make a class. And since Verac is so simple, from bytes is just returns an instance of the class. Like, this has no init method. You know, there's no, remember, like this. It doesn't have an init method because every one's the same. You actually can't, every Verac message is exactly the same. Different instances of Verac will contain no unique information. So that's how it works. And we still want to be able to do the same thing with Verac, right? Like, take a Verac and turn it into a packet. You know, we want to be able to say, to always kind of do the same thing when we're creating these packets. So we'll add a 2 bytes method here too. And it just returns an empty byte, or an empty byte string. It just doesn't have any information in it. And so this is how Verac works. And now we're at the end here. We're like, boom, this is our handshake. We can actually do the entire version handshake, right? So up here is like, let's just create the version message and let's create a packet, and with whatever variables we want, right? We already kind of saw that at the beginning of the class. You can kind of inspect it on your own time, but it's pretty straightforward. Okay, let's create a socket so that we can connect to our peer. Let's use that socket to connect to our peer, right? The argument of this function is going to be address. It's just a tuple with IP and then port. And so that is going to make a TCP connection with them. Let's send our version message. Let's send our version packet, 2 bytes. Let's serialize our version message and call 2 bytes. So our version packet will be serialized and sent using this code. That make sense?
Yes.
So there you go. There we use the word serialize, so we know where. This is why we did everything. Look, now we don't have to hard code anything anymore. We can do whatever we want. And so we send that serialized packet. And now here's the other thing. Remember, we were so yeah, we did this last time actually, right? So we've done this before. Like, let's read a packet out of the socket and then read a version message from that packet, from the payload. So we've done that before. But now here's something new. Let's read another packet, and that'll be Verac. if you remember, like after we get their version, they'll also send var_act to say that they got our version. And so we'll also get that. So now we're doing something we didn't do in lesson 2. Let's read for var_act and let's print that out. And now the last step of the handshake is let's send our var_act. Let's say, hey, I got your version message, right? Because we did. We got their version message. And so all we have to do there is we just create this empty var_act, and we just do the same thing we did before. Create a packet using the command from the var_act and the 2 bytes. Remember, which just makes, it's just that. It's just empty. So, and then we send that off. So, and at the end we return the socket because, you know, after we do the handshake, we'll want to use that same socket connection to do new things. So, if we run that, okay, as you see, I was experimenting a lot. So to make this work, run down a couple cells and copy this address. You just copy that address and just stick it into any, you'll just want to stick that into any time we call handshake. Little bug, sorry about that. So if we run it, and this is just a bug of me live coding. So if you see what happens, like look at that.
Oh.
We got their version and we get their var_act, and then it returns this live socket. This socket is connected to it's got a remote adder of that. It's connected to this guy, and we could continue to receive messages. So what's next? Well, shit, let's do a handshake, but let's just say, well, true, receive a message and print it out. Let's just receive messages forever until we kill it. So if we run this, you'll see, boom, same version message, same var_act message, but here, look, send adders, or send headers. This is a new message. Send CMPCT. I don't know what that even means. He sends it twice. Why does he send it twice? Who knows? This one's got one bit is different. Here's ping. Here's adder. He's telling us what his address is because there's just one. Here's get headers. This says, I think he wants us to give him headers, not full blocks. I'm not sure. So as you'll see, there's all these different ones at the beginning. And if you run a little longer, and I'll give you times if you guys haven't figured out how to run it yet, just check this out and I'll make sure you guys ran it. If you watch a little longer, see these, now there's these inv messages, inv. Basically, after a certain point, they're all inv. And inv is inventory vector. It's basically like your remote peer saying, hey, I found out about something. And inventory vector can basically be all kinds of different things. If we look at the protocol documentation again, look at inv. So it's a var int of these inventory vectors, and each vector has a type and a hash. And so the different types and hashes are either error, like there's some kind of error, or there's a transaction in there, or there's a block, or there's a filtered block, or there's a compact block. So these are all the different types of things that could be hidden in these inventory messages. As you see, look, I just went over there now. There's all a bunch of more of them. And so yeah, so this is kind of how what a full node does, is it just sits here connected to a bunch of people getting these transactions. Like these are probably just some random person just made a Bitcoin transaction. And these are the Bitcoin transactions propagating around the network. And so I'll say, so here, look at this. This is important. So all of a sudden, in the midst of all these enums, here's an adder. And so this one is a little longer than the previous one. This actually has 2 addresses. So this is going to be, so like if we want to run, like on the way to doing a full node, we're going to do like an intermediate project that's like a network crawler. It's just going to crawl across, it's just going to connect to nodes and ask them for their addresses, the addresses they know about, and it's just going to connect to those addresses. And so that's what we're going to do. We're going to wait until we get one of these adder messages, and then we're going to decode this and follow it. we're going to follow these addresses and try to connect to more nodes. And so that's what this is. But before that, anybody have any questions about what happened here?
It was pretty cool.
It's just protocol, right? It's trade message per rack, and then start to.
Yep, start listening.
Yeah.
Yeah, it's cool. And so yeah, the thing that's next, and now this is where, you can tell I kind of ran out of energy or time. But so I wrote this function called simple crawler, right? This is ungodly ugly, right? This piece of code. Nested while loops, okay, that's not usually what you want. It's pretty ugly, but it actually works. So the first thing it says, like, every time it connects, it says we're waiting for an error. Well, this should actually probably be. So, okay, so basically we start with a list of these addresses and basically say, while there are any addresses, right, like len of addresses will turn an integer. Oh, we could actually do while addresses, because so basically while this isn't empty, let's do loops and just basically iterate over all the addresses, right? So the first thing we do is we pop out an address. We basically remove an address from the end of the list so we can go try to connect to them. And so we'll say, hey, we're connecting to them, and we'll do a handshake, and we'll return the socket, right? This is why we return the socket. And so then we'll say, hey, we're waiting for their adder message. We're going to try to connect. We connected to them. Now we're going to try to wait until they tell us an adder message. We're going to set listening equals true, and then just basically do a while loop and say, okay, while this listening attribute is true, we're just going to keep looping again. And so what we're going to do is we're just going to listen for a packet on the socket, and we're just going to check the command of the packet, and we're going to see if it's an adder command, right? So so this is what it looks like. And so it's just a varint of addresses. So this is to, yeah. So we're going to read that and like just say, okay, if basically this is a hack. Like sometimes they just send you their own address. It's kind of weird because it's like you're already connected to them. Why would they tell you what their address is? It's just kind of like a silly thing. So this if statement basically just blocks out when they're only telling you their own address. And otherwise, let's say, hey, we received this many addresses. And what we're going to do is we're going to take this addresses list up here, and we're going to extend it with some new information. And we're going to set listening to false. So basically, we're going to stop this loop. And so this will cause the loop to go to the next round and pop a new address off. Does that make sense? So this inner loop is just going to wait until we get an adder message, and it's just going to extend this list, and then it's going to leave this inner loop, and then this outer loop is going to go on to the next address. So if we run this, oh, you gotta kill the, if you hit I twice, it'll kill this. This one was still running for me. So if you hit I twice, that'll interrupt this process. And you can tell if they're the little stars over here, remember? So what did I do? Did I do that? Oh yeah, I just accidentally broke it. So if you run that, like it'll do the handshake and it says, okay, waiting for an adder message. And then it says, oh, okay, so I actually, this if statement received adder message with only our peer's address. So that's what he said. First he sent us like, hey, here's my address. But that's not any help because we already know that address. So we're just going to continue to sit and wait here. And it's kind of annoying. Like, as you see, this program's not very fast, right? Like, in terms of, you could probably do thousands of TCP connections in the time. We could have done the handshake like 1,000 times in the time that it took us, that we're still sitting here and waiting. So if we wanted to crawl the entire Bitcoin network and connect to all the peers and like, see what version of the software they're running and everything, that would take a long time, wouldn't it? Given that we're still sitting here and waiting for them to tell us about their address. And so if we sit here and wait long enough, eventually they'll tell us more addresses. And I actually think, let's see here. Send, what is it? Send, there's another thing we can do that'll maybe make them tell us quicker. Send adders or get adder. Okay. If we wanted this to go quicker, we could do this. How do we, what is it, encode command? Yeah. Sorry, little live coding here. So if we wanted this to go a little faster, we could send one of these, where was it? Get adder? This get adder message. This just says, hey, tell us about your active peers. They tell us about your peers. And so, yeah, we're still waiting. So we should probably do this. So right after we finish the handshake, we're going to say, hey, tell us about your peers. And so if we hit I twice to kill that and run this again. Oops. Forgot my commas. Send takes no, oops. Okay, so that should actually work. Okay, so we sent them a get adder command here. And that's weird. So I just got an error saying the checksums don't match. Okay, maybe we shouldn't try to do this on the fly. But basically, if you run this long enough, eventually they'll send you about more peers. You just run this for like 5 minutes. And eventually they'll tell you about some more peers that they discover. And you'll be able to crawl the network and kind of connect to them. And so we don't need this. And so that kind of gets us to lesson 5. Like what we're going to do, what I'm going to teach you how to do in the next lesson is if you go to develop and if you go to, actually, I don't know if I even pushed this.
Yeah, I'm not seeing that.
Yeah, I haven't even, so develop, so this is like me, all my stupid little experiments. And so, not simple crawler, we want threaded crawler. So like this is gonna be a little program that, actually this is not, this is a shitty version of it. Okay, I'd have to change branches right now, but we're gonna make like a crawler that is actually fast, that can open like 100 connections up at the same time or thousands, depending on, we can optimize it so we can open up tons of connections at the same time. And so even if these things take a long time to connect like this one is, oh, so here you go. So look, received 1 new adder and boom, it connected to them. Or it tried to, maybe the connection failed. But see, that's what it's doing. It's kind of like going to slowly jump from address to address. And so I'm can show you how to write a threaded, like a really fast version of this that can, like, I ran it overnight and I connected to like, I think like 5,000 peers. You know, like I connected to half the Bitcoin network, which is pretty cool. And so the reason why that's important is it's going to teach us how to write. It's going to teach us how to do a bunch of concurrent connections and to download a bunch of information at the same time. And that's going to be important when we're doing initial block download. Basically, we're going to be able to need to be able to connect to a lot of different people at the same time. And so that's kind of a warm up, is going to be writing this little network crawler. So yeah, that's the end of the lesson here. Any questions?
Cool stuff.
Yeah.
Glad
Cool
you liked
lesson.
it. Yeah. So the next one is going to be really. That's the one that kind of wiped me out as I was learning how to do all this many connections at the same time. And when you get that working, you feel like a god. You feel like, oh my, God, coolest thing ever. So yeah, well, I'll kind of stop sharing my screen here, but yeah, so that's it. And yeah, so we'll do that on Saturday and Sunday at the same times, and it'll be fun.
See you guys.
Yeah, good.
Nice to see you.
Thanks for joining us.
Have a nice day.